All right. Well, thank you everyone for joining us today. My name is Chris Burrows, and I've been with Price Industries for over 7 years now, and I am supported in co-presenting this discussion with my colleague Ryan Compton, who will also introduce himself in a couple minutes here. So today we're going to be talking about different room air distribution strategies and some sort of quick tips and different rules that we usually apply in the field and things that can be considered when designing with these different strategies. So as I mentioned, I've been with Price for a couple of years, and I'm currently the product manager of the chill beams, systems, underfloor air products, and displacement ventilation. And so I'll be talking about specifically the stratified air systems in today's discussion and going through those in a bit of detail. And so with that, I will transfer it over to Ryan Compton.
Thank you, Chris. Yeah, my name is Ryan Compton. I am the Application Engineering Manager for GRD Products. I've been with Price Industries for almost 20 years now, but in the industry for over 20. During my time, I've had many different roles, whether it's in product development and a few different product lines, the noise control product line, air moving for a long time, and involved in product development and technical support for all of those products. So I would like to get started. We got lots to cover here, so I'd like to get started on the class itself. The course description for what we're going to talk about today is going to involve, there are many different approaches to providing heating and cooling and ventilation air to indoor spaces. What we're going to look at today is different strategies for conditioning typical commercial and industrial spaces to ensure thermal comfort, good indoor air quality, and energy efficient solutions. The learning objectives will be to increase our knowledge of overhead mixing ventilation system design approaches to address common challenges within a typical commercial and industrial space, present a variety of underfloor solutions that will allow engineers to select the best approach for any typical zone on further projects, and understand how displacement ventilation systems can improve indoor environmental quality while reducing the energy consumption of a building footprint. The agenda, I will be covering the overhead mixing ventilation systems, looking at locations of return and supply outlets, acoustical considerations. Chris will be taking the stratified air systems, displacement ventilation, and underfloor systems. So let's get right into it. So what we have here is a typical overhead mixing air ventilation system. It is called mixed air system because that's exactly what it's supposed to happen. Fresh conditioned air is delivered to the space through air outlets located in the ceiling, or in some cases the high sidewall. The air from these outlets is supplied at high velocity, which entrains room air, causing air motion and mixing with all of the air within the room to condition the entire space. So even though we are delivering air at or near the ceiling, it is the occupied zone that we are typically most concerned with. And the occupied zone is defined as 6 feet from the floor, 1 foot from internal walls, and 3 feet from external walls. And so that, when I say occupied zone, that is the space that I am talking about. If we look at a diffuser in a ceiling, this image here, we have a ceiling diffuser providing air in a horizontal pattern. We would expect it to travel along the ceiling and then down the wall. Our goal is to select a diffuser that will be no more than 50 feet per minute as it reaches the occupied zone. We do this to avoid drafts in the occupied zone, which is considered undesirable by most. So if we look at a typical space, what I've decided to use here is a 400 square foot room. 9-foot ceiling is pretty typical, and we're going to have 1 diffuser in that space. there are hundreds of ways to deliver air into the space, and the number of outlets that we have available is numerous. So we're not going to go into great detail about different products. That's certainly what the website and the catalog are there for. But when I talk generically about radial pattern from a diffuser, I'm looking at square cone diffuser or a square plaque diffuser that has equal throw in all directions. Typically, that radial pattern is going to be a shorter throw. We're also looking at something like directional diffusers. Now, a directional diffuser is available to provide air in one-way, two-way, three-way, or four-way, and typically has longer throws. A directional diffuser often is going to be a little bit louder than a radial diffuser, so that can factor into our design considerations as well. Depending on what's happening in the space, sometimes you need more air changes per hour. Sometimes, the loads or the number of people in that space are going to dictate needing more diffusers. So if we have that same space and now we're going to 4 diffusers, we're going to use, a similar approach when we have multiple outlets, and that we have, excuse me, when we have multiple outlets and that horizontal airflow pattern collides, the air will be directed down towards the occupied zone. This is desirable to get the air into the occupied zone, but like what we saw with that single diffuser example, we want to have that throw at 50 feet per minute as it reaches the occupied zone to avoid drafts. So here we have diffusers. Ideally, we want them spaced out evenly, and we want to select that airflow pattern so that it overlaps slightly, ensuring that we're not exceeding 50 feet per minute in that occupied zone. If for some reason we're not able to put the diffusers in the locations that we want and closer to the center of the room, whether that's lighting, sprinklers, AV equipment, any number of things, another approach would be to maybe put directional diffusers on the external walls or closer to the external walls and have them directed toward the interior wall to get air mixing and condition that space. However, for smaller rooms, directional diffusers can sometimes have too long of a throw. So something that we could look at is high induction directional diffusers. Directional diffusers with mixing vanes in them encourage room mixing, and that's why they're referred to as high induction. The high induction diffusers will have shorter throws, which could help in some situations, as well as in the Northeast. This type of selection is pretty popular. Heating and cooling loads, more induction is desirable, and I know that it's quite common in the Northeast territory. So that was diffuser selection, air outlet selection. Now I want to look at return air inlet selection. A lot of thought is given to, or more thought is given to supply diffuser location, but we know that we need to have a return air somewhere in the space, but oftentimes not a lot of consideration is given to where exactly that is. So I would like to look at some scenarios in terms of that return air inlet. Now, ideally, we want to install the return air inlet in a space where there might be stagnant air, or maybe there's a heat source such as a photocopier or a coffee maker. Those would be ideal locations for that return air location. What we do want to avoid is putting that return air inlet directly in the path of a supply diffuser, because that will result in, or can result in, short circuiting. So basically the air comes out of the diffuser, back out the return, never gets into the occupied space. We're not getting our fresh air, we're not getting our mixing when this occurs. Another scenario could happen is if we locate that return too close to the diffusers, we can actually have high velocity air coming across the surface of that diffuser, almost acting like an air curtain and preventing air, the return air, from getting into that inlet and out of the space. This is referred to as shearing. When we're doing heating from above, this can present a lot of challenges when it comes to return air. And ideally, if we are doing heating we might want to look at other locations for that return inlet. The warm, buoyant air is more likely to short circuit and not get into the occupied space. One solution to this is putting the return on the low sidewall. If we locate that in the low sidewall, that air is allowed to travel down the wall, get into the occupied space, and create that mixing that we're looking for. So when we look at return air locations, we have this example here again with the 4 diffusers. Where would we put this? You know, in a corner somewhere is a common place. You know, that's likely where we're going to have our stagnant air. It's the furthest away from the diffuser that can be located in this particular scenario. If you're still directly in the path, or for some reason it can't be installed there, you know, sidewall applications could be considered, but typically sidewall is a little bit more complicated and adds a little bit more cost, and that's often why we see them in the ceiling. Depending on the type of diffuser that you're using, it doesn't necessarily have to be located in the corner. It's not always got to be in the corner. And in an example of these directional diffusers, these high induction directional diffusers, having it in the corner would be in the direct path of that diffuser. So locating it more towards the center of the room where there's likely to be stagnant air is probably a better location in this scenario. Next, I'm going to shift gears and talk about some things that can impact our throw performance. So, Coanda effect. This is a term that's used quite a bit in the industry. And what does it mean? Well, Coanda effect is used to explain high velocity air that comes out of the diffuser when it's installed in a ceiling system. When that happens, a low pressure zone occurs at the edge of the diffuser, causing that air to cling to that adjacent surface. Typically, catalog performance for ceiling diffusers is going to include this. So the assumption is that the diffuser is installed in the ceiling. If we have a diffuser if we have a diffuser installed in a space that has no ceiling, what does that mean? Well, we can expect that throw to be reduced by roughly 30% just because there is no ceiling. So that is something to be mindful of in these spaces. It's becoming quite popular to have that industrial look where we have exposed ductwork and no ceiling. We need to understand that that is going to impact the performance of that particular air outlet. Another thing to consider is architectural features or support structures that may be in the ceiling and what impact they could have on our airflow pattern. We could expect Coanda, we should expect Coanda to still occur if that angle is less than 10 degrees. So basically, if we look at, the angle of the air coming out of that diffuser and to the edge, the bottom edge of that obstacle or obstruction, if it's less than 10, we can assume that the air pattern will be maintained. If that obstruction is larger, it can result in a loss of pattern and basically airflow being directed down into the occupied space, which again can create drafts, which is undesirable. So what do we do if somebody plunks a architectural feature right in the middle of our room? One approach might be to use directional diffusers. We can put them along the architectural feature and direct air away, still getting our mixing within that room. But another solution that is quite popular is the idea of a slot diffuser. Linear slot diffuser that could run the length of that architectural feature. Architects are typically more fond of this approach because it does add to that feature in the space. It can accentuate it. But the assumption is when we have linear slot diffusers is that the entire diffuser is going to be active and that it will all supply air, which is not the case. In fact, we can blank off sections of this diffuser. So it looks like one continuous run, but sections of it would be blanked off. This allows us to provide smaller sections of diffuser with longer throws that can help us with our mixing. The other benefit to this is our return air location. And we can actually locate return inlets in that same slot. If we locate the returns along the perimeter of this space, that can result in short circuiting. So having them in parallel with that supply diffuser is actually often the best location for that return. If there is absolutely no room for diffusers in the ceiling, a sidewall grill might be an option. And this is popular in condos and hotels, in the idea that the grills would be located in the sidewall. They're available in single deflection and double deflection, and they're located on the sidewall and they project horizontally into the room. When we look at the throw from sidewall grills and the deflection associated with them, we can see that zero deflection is going to give us our longer throw. But as we add deflection to that grill, we're going to see that that airflow pattern widens. And so when we got a 45-degree deflection, we're going to end up with a much wider and shorter throw, which gives us some flexibility in terms of laying out our space. When we're using sidewall grills, ideally we want them located within 18 inches of the ceiling so that we can maintain that throw. If that's not possible, the idea of using either double deflection or single deflection grill to direct it up towards the ceiling can help us maintain that throw that we're looking for, projecting it up towards that surface. So if we come back to the space and somebody has decided to add a window that we need to condition, what is the best way to approach that? Well, a lot of times it's going to be with a slot diffuser. In fact, I believe it's the ASHRAE applications handbook that states that this is the recommended solutions to provide that slot diffuser along that vertical wall. And when we're installing these types of diffusers, to maintain that vertical throw, we want to locate the slot diffuser within 18 inches of the window so that the air clings to that vertical surface. This is more important for high ceiling applications where long throws are required. Typically with 9-foot ceilings, throws will often be too long and we can cause drafts along the floor, and this could be felt on the feet and ankles of the occupants, which is obviously undesirable. If the throw will be too long, we could move the diffuser away from that wall and have it project horizontally towards the window. As it hits the wall, it will increase the spread so you get better coverage over the vertical face. And depending on the loads within the space, if they're low, we could potentially get away with fewer diffusers by doing this as well. So if we're looking at our 400 square foot space, typical lows, 9-foot ceiling, 1 slot diffuser, we could expect, based on mock-ups that we've done, that space should condition about a 10-foot space away from that wall. If you have a larger space, you may need to go to a 2-slot diffuser that also has a horizontal projection, so 1 vertical, 1 horizontal, or we could look at using separate diffusers in that internal zone to condition that space separately. When we're looking at return locations for these vertical slot diffusers, in the corner is often location in line with that slot diffuser. So again, out of that direct airflow pattern, we want to locate it in a spot where we want where we might see stagnant air. Another solution, and one that might be a little bit more architecturally appealing, is to extend that linear slot and have the returns on either side of that supply. So I spoke about the thermal units, spoke about the diffusers being tested in isothermal conditions. Isothermal conditions mean supply air temperature and room air temperature are going to be equal. In vertical applications, when we're looking at heating, we're going to expect that throw to be decreased. Again, based on some research that we've done, mock-ups that we've done, we apply a general rule of thumb of 1% per degree Fahrenheit. That means if we have 90-degree supply air, we could be looking at that throw being decreased anywhere from 15 to 20%. In cooling, we're going to see that throw vertically extend, again, by that 1% per degree Fahrenheit. So if we're looking at 55 degree supply air, we would expect that throw to increase 15 to 20%. So in perimeter zones, we often need to provide both heating and cooling, which can provide challenges for diffuser selection. The impact of warm air versus cooling air on the diffuser throw often means some type of compromise. You know, a common approach is to size the heating throw for 2/3 of the way down the wall and limit the cooling to 2 feet along the floor. Since the occupied zone is considered to be 3 feet from an external wall, the typical, that's typically considered acceptable. An alternative method that we can look at is the idea of just using isothermal data from our catalog and selecting that heating throw based on 150 feet per minute at the wall. And then for the cooling portion, we would look at throws to be 50 feet per minute at the floor. Now, rarely does it work out perfectly, but if we're looking at a typical space, this is a rule of thumb that could be used. So we looked at vertical throw. The same is true for horizontal throw in terms of isothermal. Performance data, catalog data is typically always based on isothermal conditions. But in this case, when we have heating flows, we're actually going to see that throw extended, and we would expect it to be similar, 15 to 20% for 90 degree supply air. And in cooling, in horizontal, it's going to actually shorten our throw now, and so we're looking at 55 degree supply air. We would expect that to be decreased from isothermal catalog values by 15 to 20%. So if we look quickly at horizontal application where we have cooling, where if we assume the same airflow, we would expect a much longer throw in heating than we have in cooling. Now, if we look at typical applications, if we're doing reheat, ASHRAE 90.1 would tell us that we typically look for an airflow above a reheat airflow of about 50% of our max cooling. So by reducing that airflow, maybe it's not as big of a concern in horizontal. Next, I'm going to switch gears and we're going to start talking about acoustics. So the idea of what is my acoustical goal here? And ASHRAE Application Handbook provides values. I think this one's actually out of the Price Application Handbook. And we have a number of different values here for different spaces. NC values are so ingrained in the industry and the most common. It also does list RC values typically. RC values are similar to NC. They use a slightly different curve and involve a few more steps, but when it comes to selecting GRD products, it's almost always NC values that we're talking about. But if we look at typical spaces of private residence, NC 25 to 35, and that's pretty typical of a lot of spaces. But when we look at something like a teleconference room, and those are becoming more popular with all our Zoom and Teams meetings, and so the idea of really critical sound levels less than NC 25 for those types of spaces because of the microphone, the audiovisual equipment that's being used in there that will pick up background noise. Typically, we're looking for lower sound levels. And then corridors or lobbies, much higher, NC 40 to 45. And in some cases, background noise is actually desirable to mask those conversations and other noises that might be happening in those spaces. So something to consider when you're selecting the diffuser, that it shouldn't always just be NC 25. We should look at where it's going. What we have here is the catalog data, sound values at a number of different flows. And I want to point out a couple notes. One is NC values are based on a room absorption of 10 dB. So basically that's saying that the room has 10 dB of absorption. Now, if you have a space that has hard surfaces, lots of glass and concrete, you might not have 10 dB of absorption. If you have a more absorptive space, it might be a little bit better. But it's important to understand that that assumption is being made in these values, and if your room deviates from that, you might want to have a closer look at the sound performance. The other thing that I want to point out is the blank spaces. That when you see a dash, that actually indicates that NC levels are below 15. And when that occurs, that means that basically background noise is too high for this to be accurate. And the reality is, if you're designing a space for NC 15, we probably should have a more detailed analysis and look at sound power values and the actual space. And that's why that limit is in place there. So we looked at one outlet. What do we do if we have multiple outlets? How does that impact my sound? And this is a table, again, I've seen it many times in ASHRAE documents. This one happens to be from the price handbook, and it looks at the number of outlets and what impact that would have. How much does it increase the sound level in the space if I have more than one diffuser? So if I have 4 diffusers, all selected for NC25, I would sum those up, and it would be 6 dB higher. So those 4 NC25 diffusers result in a sound level of NC31 in that space. If we look at this space and we put somebody in that room, what is their distance away from it? Well, ASHRAE AHRI 885 assumes, a distance of 5 to 6 feet away. So in a room of 400 to 600 square feet, we can assume that they are, roughly that distance away, or within proximity that the sound generated by that source impacts the end sound level. If we double or even triple the size of this room, we're going to see, maybe that next diffuser might have some impact depending on what else is going on in the room, what type of diffuser it is. But the reality is that diffuser that's 50 or 60 feet away is not going to impact your end sound level that one occupant is going to observe. So typically, even in these larger spaces, we could simplify it and look at a space of 400 to 600 square feet for a sound estimate. Now, if we're dealing with sound sensitive spaces, critical spaces, we might want to do a more detailed analysis, and certainly there's acoustic predictive software that can take a look at your various sound sources, your room characteristic, and apply that appropriately to get a better understanding of what the sound levels in that space will be. Before I go, I do want to hit quickly on the idea of inlet conditions and how that can impact sound performance. So ASHRAE 70 is assuming ideal inlet conditions. If we have less than ideal inlet conditions, we can expect that sound level to increase up to 12 dB. So that's more than double your sound level. And whether that's an abrupt turn into the diffuser, or whether that's flex duct that's not quite straight, we need to take measures, whether that's ensuring that flex duct is straight, or putting something like a flow equalization grid in to help out with that. And the last thing is damper position. So the idea of where is that damper located within that diffuser, this can impact our end sound result. The simplest place to put it is at the outlet. It's a lot easier to access there, but we can expect that sound level again to almost double. We're looking at up to a 9 dB increase by putting it at the air outlet. A better location might be in the neck of the diffuser with a cable operator. But if we can move that further down the ductwork, that would be desirable from a sound perspective, as we expect it to have no impact on the end sound result. However, locating that damper downstream typically means that you're going to need to have an access door in the ductwork, which isn't always an option, and there might not even be space to get that damper in there 5 feet downstream, but something to be mindful of. That's all that I have for mixed air systems. I'm going to hand this over to Chris and let him talk to you about stratified systems.
All right, excellent, Ryan. Thank you so much. So yeah, this next section of the discussion is going to be on stratified air systems, which, as you know, is quite different than the systems that Ryan was talking about. We're actually going to promote stratification in the space. So we'll kind of chat through how that's going to work and the different approaches based on the application that makes sense. So getting right into it. All right, so again, first off, just comparing to an approach that Ryan was talking about. The idea here is actually we're not dealing in worlds of really throw anymore. So we're gonna try and to really test you today and get you to think about a sort of a different approach as well. Looking more at a buoyancy-driven, naturally, convected space. So in this scenario on the right, where you're looking at displacement ventilation, we're going to let the air fall into the space that is, around 10 degrees cooler than the set point in the space. And from there, it's going to kind of fill out the space evenly and be pulled up across the heat loads themselves. The idea is that you have direct supply of the fresh air directly into the occupied zone, but you're also letting any contaminants associated with the heat sources be lifted up above the space and pulled out through the return instead of being entrained back in. So to give you an example of what that looks like, so this is an example in the tech center down here in Suwanee, Georgia, where I'm located, and you can see we've got the air coming out around 40 feet per minute, and it immediately is dropping due to the buoyancy difference. And from there, it's being immediately seeked out or pulled across the room, not thrown by the heat sources themselves. And so I'll kind of show you, I'll let that play once more here. Let me see if I can start. So it's a little bit choppy, but you can probably see that the air is moving already a foot or two quite slowly once you get away from the diffuser. In fact, the thermal plumes, we're used to feeling a certain air velocity across our bodies. And so what you find with these systems, it's a very flexible, comfortable system. The occupant on an individual level in the space is actually driving the air movement throughout the space itself based on that particular person's heat output. All right, so with respect to that, in terms of indoor air quality, there's a lot of studies out of there that compare it to a uniformly mixed system. And what we have here is air change effectiveness is one of the metrics that was looked at this Young and Zeller study. And essentially that is looking at the ratio, comparing the time it takes for the supply air to get to the breathing zone with reference to the time it takes the supply air to get to from the supply point to that return location. So as you would expect, especially from that video, it would the supply air would get to the breathing zone quicker than it would take to get to the return zone. And so it's essentially what this is noting, about a 30% improvement in those travel times by the UFAD or underfloor air distribution system and displacement system compared to a mixing system. And that's the overhead mixing system is essentially driving that air movement and very rapidly inducing and mixing that space. And all the momentum is essentially from that diffuser in the space. Whereas here, we're really letting the thermal plumes provide the air movement in the space. Again, so about a 30% on average. There's a couple of local peak ACE measured levels, and that's likely due in most cases to the thermal plumes themselves drawing a lot of those air changes. And then operating costs. So as you would probably imagine, the difference from the ceiling supply system trying to push the cool air down to the lower level, instead this is essentially delivering into the space and letting the, again, natural convection kind of drive those the air throughout the space. So what happens is the static pressure is around 0.05 inches or less water column across these diffusers, which can really help, at least from the terminal device's point of view or diffuser's point of view, lower some of that system static pressure and ultimately result in lower fan horsepower required by these systems. Now, depending on where you're kind of designing for, there's certain climates, and in fact, anywhere outside of kind of the southern or southeastern US, there is opportunity to provide additional free cooling hours and economizer hours by the elevated supply air temperature, because now we're supplying into the occupied zone. Usually we're supplying around 63 to 68 degrees on average, somewhere in that range, to cool the space. So that gives you around a 10-degree bump of opportunity throughout the year to free cool the space, which of course more fresh air, 100% fresh air is going to lead to a lot of indoor air quality benefits as it relates to the occupant wellness and learning environments if you're looking at an education application. So again, because of those items that we talked about earlier, with lower static pressures required to push the air into the space and lower air speeds that are typical, a lot of times we see applications like concert halls or auditoriums where it's very noise critical spaces. You had seen the NC levels that Ryan was sharing earlier, where you're trying to get down to NC 25 or 20 or lower. These are very commonly utilized because of that. And so oftentimes you can put for very wide spaces, more than 60 feet is kind of the typical rule that we like to follow. You want to get the air to the middle of the space, and oftentimes you'll see round floor diffusers placed underneath every other seat. And that is essentially enough air in most cases to supply and condition that entire room. So that kind of solves a lot of design challenges. If you're trying to provide diffusers in the ceiling or hide behind the architecture for a fully mixed system, this allows you to tuck it away from sight underneath the chairs and provide displacement relation approach to the space. So again, about every other seat is typical. The round floor diffusers supply around 40 CFM at 0.04 inches of static, 0.03 inches of static, which again helps keep the noise down. There is a combined effect, like Ryan was talking about. So if you have a lot of diffusers pretty closely coupled, so you just want to select well below NC 20 and NC 15 even when that starts to register on a manufacturer catalog data. So that way the combined effect is not up near that NC level versus limitation. All right, so now we're going to get into defining an underfloor air system and basically what this system looks like from the ground up. All right, so here we've got our perimeter facade system, and essentially you'll, just like any other space, you'll have your centrally located core facilities, your IT, mechanical room. Here instead, you're going to have basically, let me pause it here real quick. All right, so in the case of the centrally located mechanical room, where you might have a horizontal compartment unit, you've got your outside air shafts that run down through the building if this is a multi-level space, and either supplies into this mechanical room or is ducted directly to the air handling unit. Now, because with a multi-story underfloor air system, and you've got your return air path is on the bottom side surface of the supply plenum on the upper or the floor just above, you do get thermal decay. And so there is some heat transfer up into that supply plenum. You don't want the air to travel that far, from 60 degrees from the mechanical room out several hundred feet to the perimeter space. So if you have a design like this, you will want a little bit of ductwork to essentially get the coolest air to within about 50 feet of the perimeter space. So the other approach is to go to a vertical fan column. Sorry, it's kind of jumping around here. So just jumping ahead. So the vertical fan column approach right here, where essentially we're going to put the fan columns within their own closet. And these closets are really small, typically 6 foot by 6 foot or 8 foot by 8 foot. And what you'll find there is that the air supply point is now much closer to the perimeter zone. So we've gotten rid of that horizontal single air handler unit in the middle there and actually shrunk the core size and pushed those fan columns into a very small closet into this space. So then this removes a lot of the ductwork that you need even under that raised access floor. So what you could have if you don't have that ductwork underneath the raised access floor, you could essentially reduce the floor height. So I'll continue playing this one here. So typically you'll have your home runs for the power and distribution for, say, plugging into the floor for your workplace, your workstations. If you want to plug in furniture, especially modular desks, all of that is kind of located throughout the floor plate through plug and play connections. The other device that's typically installed in the raised access floor are your data consolidation points. And so this is going to transfer all of your IP and your internet, as well as phone over IP if voice over IP, if that's what's being used. And so all of that is through a room side accessible distribution box. Now there's manually adjustable baskets as well as automated baskets for your enclosed private offices or conference rooms. And then also there's linear natural convective heaters that are used along the perimeter. So that can provide your cooling as well as your heating in the space. And again, in heating, that's all using room recirculation, natural convection. So we'll walk through each of those zones, but to kind of show you how this is built up, that's what's typically used in underfloor air systems today. All right, so again, this is kind of what you would see with the fan column approach. And the real benefit here is that we're moving it into a small closet. The opportunity here to save 200 to 300 square foot back per floor is what we've kind of seen in practice. So using a conservative $20 of rent per square foot would yield several $1,000s per month of floor by going with this type of approach. And again, it puts all that cool air much closer to those perimeter extreme areas in the space where you need that cool air. So this is a bit of a top view of that mechanical space with that downward discharge vertical air tower unit. And typically you can put a single duct box here and a damper that controls your outside air to the mechanical closet. And so that can be used to either open or close the amount of fresh air that's being provided to the space. And that can just simply dump into the mechanical room and be pulled into the air tower and mixed with the return air and can be essentially filtered or other clean air technologies kind of integrated into this vertical air tower to then mix and provide that clean air down into the raised access floor. Okay, so moving away from the mechanical space into the occupied space, we most often have manually adjustable diffusers in the raised access floor plenum. Here you can see this particular arrangement is not ducted. It's just being supplied through that pressurized floor plenum. Now, in comparing to a ceiling mixed air system, like the type of approach that Ryan was talking about, you'll have a round floor diffuser about every 80 square feet for at least an 8-inch diffuser, one every 80 square feet for an open office, typical open office type of a load. And again, these are manually adjustable, so that way you give an occupant or every 2 occupants the ability to adjust their flow rate simply by reaching down and rotating that face in the floor. So in terms of flexibility is the next part that I want to talk about, and I'll kind of skim through here for the sake of time. So again, that's pretty much what you would see in a underfloor air system. is a clean floor, not a lot of sort of obstructions underneath there. And you've got your zone distribution boxes transmitting the power as well as the data. And as we shift in kind of the typical design of an office space that we see, at least had seen in the last several years, from completely open office and shared spaces to now going to more enclosed spaces like what's shown here. So this owner had a requirement to go to a conference room and 3 private offices. And so we're going to show you kind of how this space would move around and provide the flexibility of an owner or a developer in their building to be able to adjust to those changing demands in the workspace and the businesses that are either moving in and out or adjusting to the new requirements that might come out for either through the local codes and standards or even the adjustments by the company. So notice we're using existing materials here from that open office plan. We're going to move the round floor diffusers and replug in the perimeter heating devices into that control module. Here we're going to use the existing diffuser face and ring and drop in new VAV baskets into those rings that are mounted in the floor. And so that way you get VAV control. It's all plug and play wired back to that control module, and then ultimately controlled through a thermostat. In most cases, you'll have a lot of the wall structures mounted above the raised access floor, so you're not making any penetrations down into the actual pressurized air plenum. Transfer duct, as seen up above the doorway here, back into the open office. And same approach kind of occurs with the individual private offices there. So you saw the round floors move into their new location and get a VAV basket. So that's a little bit of the flexibility that this type of system provides and designing for the future. All right, so in terms of the things to keep in mind when you're using displacement or UFAD approaches, you always want to make sure that your peak design is throwing below 4.5 feet. If you're going to be using an increased ventilation effectiveness or zone air distribution effectiveness. So when supplying from the floor and not throwing above 4.5 feet, you can use a 1.2 zone air distribution effectiveness. That allows you to either get an improvement over, again, a dilution mix system, or allows a reduction in outside air through that ventilation rate approach. For really tall spaces where, again, latent load isn't really driving your outside air, fresh air requirement in the space, maybe a lobby, atrium area, and your space is taller than 18 feet and you're allowed to put that return grill 18 feet above the floor, you can actually use 1.5, which could, again, if you're comparing to a mixed system, could be anywhere up to a 46% difference in either air quality or reduction in outside air. So in terms of the different diffusers and approaches that you can take with an underfloor air system, this is a fully stratified displacement round floor diffuser. What I would say with this one is this is really going to maximize your stratification. You'll see the smoke plume is operating just like you would have with a in-wall displacement approach. And the nice thing with these is you could put them in conference rooms or private offices, directly underneath desks. These are the ones that we install in auditoriums and conference halls that are, within a foot of the occupant's ankle region. And you really minimize your draft concerns with the low turbulence that is witnessed by these diffusers. But don't be afraid to mix and match a displacement round floor with a twist diffuser. And you can put these in the areas where they're most likely required. Conference room, I say that because your furniture layout could be different day two. And so if a bunch of people run into a conference room and bring their chairs in and sit directly underneath a high throw diffuser, that's going to be pretty drafty. So this really is independent of the furniture layout. as compared to a higher throw diffuser. So kind of on that note, here's the twist diffuser that we were talking about. Again, making sure it doesn't throw above 4.5 feet at peak design. And the idea is that this one is supplying more air than the displacement round floor diffuser, and it's inducing and pulling in some of that local room air in the occupied zone, but it's not breaking through the stratification and re-entraining contaminants that are already lifted up above the space through the thermal plumes and that upward displacement of airflow. So again, these would be great for hallways, outside of cubicles, in the openings to cubicles where you're not going to have people standing directly over for long periods of time. So again, like you had seen in the flexibility video, talking about the adjustments in the space, here we can see the automated diffusers. So there's opportunity to make each one of these diffusers automated. So that way, if for intermittently loaded spaces, like an office space or a conference room, you can have those completely shut off and seal up. And those can all be driven by the thermostatic control in the space. Most everything that's installed in as it relates to the HVAC components is plug and play. So for example, the cable here is transmitting the control and power through a single cable, and everything is plug and play through quick connects. The idea here is that we're augmenting those benefits and of the flexibility of this system with the raised floor and having power and data sort of at your fingertips directly at the floor level. Now moving from the interior cooling spaces to the perimeter cooling and heating spaces, here again we've got those natural convective troughs that essentially, again in heating mode, let the air from the space fall down into those troughs and heat up and rise up and condition the perimeter loads in the space. And these are controlled very similarly back to the thermostats. The other scenario you might run into is a zone where you have VAV round floor devices, as well as the perimeter heating and cooling devices. All of these can tie back to a single simple factory mounted and sequenced controller, and everything is plug and play again to make installation simple and adjustments simple. So there's just a quick note, there's a lot of different options in terms of cooling and heating the perimeter. And it kind of evolves from the simplest form, which is your natural convective heater, to your cooling and heating device with a cooling coil and a heating coil, and then moving all the way to a integral fan force trough approach, where again, if you've got something to consider for condensing boilers, low temperature heating, such as 90 to 120 degrees entering water, you'll need a little bit of forced convection through this fan unit to essentially achieve the BTH rating per foot that you would have with a similar natural convection unit, no fan, at 180 or 160 degrees. So just something to keep in mind. There's lots of options there to condition that perimeter zone. And then of course you've got the fan box option, which essentially is just serving as a booster unit that is pushing through ductwork under the floor through these plenum floor mounted devices here. All right, and then next up is displacement ventilation. So we're going to go through a couple of different design techniques that are used with displacement. And one of the big things that we always start off talking with is the different breakdowns of the loads and how they apply to that. If you refer back to, again, Ryan's slide talking about the occupied zone, how we define that, 6 feet above the finished floor, 1 foot in from the perimeter. When you're using these stratified systems and kind of allowing the air to be pulled to the occupied zone, and you're not re-entraining and you're not mixing a whole lot of loads from the perimeter, glass wall, or the overhead lighting, how exactly do we design with these systems? So fortunately, we have ASHRAE that has done a lot of research into that, and actually many years ago now, they came out from this complex study, these nice factors that we can apply to the individual total loads in the space. Essentially what this is telling us, 30% of the occupied equipment load is applied to your cooling CFM calculation for displacement ventilation, and respectively 13%, 18.5% for your lighting and radiation respectively. All right, so now the other side of it is, again, kind of applying those different factors, and what exactly does that look like? So obviously we're not changing physics here. We're just kind of operating or changing how we design the airflow movement in the space and how we need to account for that on our cooling load calculation. So for a fully mixed space, hopefully this is all very much review for the group here, but you've got your total load here in the numerator, and it's kind of broken out with anticipation of the displacement calculation. Your occupant equipment, lighting, exterior, all over the rho CP delta T. So for this case, we're going to be comparing this fully mixed system designed that needs about 824 CFM to condition the space. But with displacement ventilation, hopefully you recognize these factors that are in front of the different heat load coefficients. And then in the denominator, we've got our delta T is actually not the total delta T for the room. This is going to be your allowable THF, or head to foot temperature differential, that's allowed by what we commonly use is ASHRAE 55 comfort standard. So they currently allow 5.5 or 5.4 degrees for a seated occupant of allowable temperature differential, or 7.2 degrees for a standing occupant. And so if you plug in all these numbers, hopefully trust the math there, what you'll get is the matching overall BTUs. These will be deducted, of course, and then what you get is 630 CFM for displacement. So again, just want to note a couple of differences there. Now, everything we've talked about up to this point is cooling related. So for heating options, of course, you don't want to heat into the space with a high delta T at low velocity. We all know that, especially from Ryan's discussion, because that's going to short circuit. That's going to cause issues with that warm air rising naturally immediately up out of the occupied zone. So oftentimes what you see here is either a auxiliary hydronic or electric system, like this linear enclosure that has a fin tube or an electric resistance heater in it that can kick on when heating is required in the space. And that is separate from the displacement cooling, which is in this case, in this enclosure, down below this mullion here. And so that will supply that displacement and cooling mode. Or you can have a ceiling radiant panel to provide heating in the space, or pretty much all of the displacement products come with a heat cool switchover option. So in heating mode, here we'll have this mounted in the ceiling for this particular product, and that will operate and throw across or directly downwards from the slide diffuser and essentially mix up the space in heating mode. The caveat to this is that if you're looking at designing, or if you're doing like a DOAS dedicated outside air system, or you're looking at downsizing your outside air through that ventilation effectiveness credit, if you're heating and using a mixed turbulent type of approach in heating mode and not one of these radiant natural convective heating approaches, you have to consider that, of course, when actually looking at your overall mechanical footprint, because now you have to consider the air distribution effectiveness in the heating mode as well. If you use one of these approaches, maintain that stratification year round, then you can actually possibly downsize your overall equipment size. So here's an example of the ceiling unit installed. So again, in heating mode, the slide diffuser would sort of project that air down towards the window and then down towards the occupied space. The other option, which is becoming more and more common, is an in-floor active slab heating approach. And just a quick note here to mention is, these systems work actually quite nicely together. And the idea is that the displacement airflow velocity across the floor is not moving quickly. And so because a lot of the exchange from that floor in radiant heating is all radiant, there's little conductive heat exchange and convective heat exchange by those combinations of those design aspects. So it actually works quite well together. There is a temperature of the floor that you're going to want to maintain a limit to, 82 degrees Fahrenheit, somewhere around there, so you're not having too much heat, and that actually ends up warming the air enough to affect it once it gets 15, 20 feet away from the diffuser. So this is an example of what you might see in a, this is a classroom shown here, about 800 square feet. And you've got two diffusers with a single duct run that's running out to each of those diffusers, 400 CFM each. They're all, looks like, at the perimeter wall area, supplying inwards to the space. The return path, you always want to place the return up high in the ceiling, because again, you're stratifying, your warmest air is going to be above the occupied zone. And so you want to always place that return up high, and preferably as close as you can to the perimeter of the space. For a classroom, this is probably about 15 feet in. That's plenty close to the perimeter zone to be able to not have any temperature gain throughout the day and have that start collecting. So really good design. This one here has a VAV controlling the air to those diffusers, and all controlled off of this thermostat located near the door. So again, upstream of the diffusers themselves, it's very similar to a overhead mixing system. Here, as an example, if there's projects that currently look at ventilation only designs, this is one example where you've got one classroom that has just one unit. It's supplying just outside air to the space. In this case, your reduction in outside air would directly reduce your ductwork and sheet metal cost impact to the project. But again, that's for ventilation only projects in case you're designing with that approach going forward. And then last thing I want to talk about is just the last change. I mentioned upstream of the diffuser, there's really not much difference as a VAV system. The one thing that is different, or is going to be different, is that supply air temperature. In terms of dehumidifying, we don't want to change anything of how you dehumidify the air for a particular climate or space. So you still want to cool it down to 55 or cooler if you're looking at that for a particular ratio in the space. But what's going to happen is you're going to have a couple of different techniques: return air bypass to bring that 80-degree stratified return air and bring that in after the coil to bring it up to 62, 65 degrees. That's an option as well, and all at the same time modulate your chilled water coil. Or you could do a package DX unit that essentially has a high gas reheat option, so that way you don't have an energy penalty. Again, bring that 55-degree air up to 63 to 68 degrees for the displacement approach. There's other sort of options that you can have with energy recovery wheels, and again, return air bypass back into the supply as well. All right, so again, thank you very much for your time. In summary, again, pay attention to the correction factors that Ryan was talking about. Again, catalog data is usually made with certain assumptions, and there are catalog correction factors that are out there that can be used for specific design goals. And then, of course, looking at equipment location, consider stratified air systems for energy savings and really helping improve indoor air quality based on unitary or unitary systems that might not be able to achieve similar results in terms of the occupant comfort level. So again, thank you so much for your time. We hope you enjoyed this discussion, and we'll pass it back over.